everyone, today let's try to solve another LeetCode problem. Today's problem is called make array empty. So in this problem, you are given an integer array nums containing only distinct numbers, and you can perform the following operations until the array is empty. If the first element of the current array has the smallest value, you can remove it, and otherwise you put the first element to the end of the array. So we need to return an integer denoting the number of operation until the nums become empty. So let's take a look at this first example. The input is 3 for -1. And the answer is 5. Let's see how that's come from. For the first operation, we moved 3 to the end because 3 is not the minimum. -1 is the minimum. That's why we cannot just remove 3. That's why we have to move 3 to the end. And that's why it becomes 4, -1, 3. And the second operation, we still cannot remove 4 because 4 is still not the minimum. The minimum is -1. That's why we move 4 all the way to the end. And the array becomes this. And now, after the second operation, -1, which is the first element now, is the minimum. So we can remove -1, and now it becomes 3 and 4, and 3 now becomes the minimum and also happens to be the first element. We can remove that as well, so it becomes 4. And the last operation, we just remove 4, which is the only element, then of course it is the minimum, and after 5 operation, the nums become empty. That's why we return 5 in here. So let's think about how can we solve this problem. Still looking at the first example and see how can we come up with a solution with that. Well, if we look at nums, and we know after sorting, we know we will visit this first, and then we will visit this second, and then we will remove that last. So if we take a look at their index, the first index will be 0, second index will be 1, and the third index will be 2. We know that we will remove index 2 first, and then we will remove index 0, and then we'll finally we'll remove index 1. So that's pretty straightforward. And we're initially starting from 0. So we initially at 0 index, and we need to go to 2, and then we need to go back to 0 again, and then we finally go to 1. That's the flow of how we're gonna remove things, or how the cursor is gonna move. But how is that relevant to the cost? So maybe I can draw a diagram so to make it more intuitive. So we start at 0, and we need to go to 2 first, which is here, and the first step is going from 0 to 2. This gap will be part of our answer, right? Because we don't want to remove 0 first, we have to go to 2 first. That's why we have to move this 0 and move this 1 all the way to the back so we can reach 2. That's why the difference of these two can somewhat tell us the cost. Basically, the gap between current and our next desired index will be part of our answer. Then what we're gonna do next? Next, we want to visit 0, right? After removing these two, it just happens that we end up being 0 index, but it could be more. For example, it could be more element here. So basically, if the next position is on our left-hand side, we are choosing the gap from the current index all the way to the end, and also the gap from 0 all the way to our next desired position. For instance, this is 0 index, but this could have been more element here. So first case scenario is that if we are moving from left to right, then that's easy. This is the gap that we are choosing from. But if we are moving from right to left, we cannot move left. We can only put things to the end. That's why we have to add this gap, which is the current index all the way to the end, and 0 all the way to our next desired position. That's the two gaps we have to consider. But there's one thing more. When we remove certain element, for example, this 3 might be removed by the time you want to move 2 to 0. So even though we are counting this gap, we don't want to count this 3. So how can we notify it? So there's one technique that we can use is calculate the dynamic range sum. So you can imagine everything at the beginning has one value in that. So this has 1, and this has 1, and this has 1, and this has 1. So when I try to calculate the gap of these two, I can just perform 2 range sum, namely the range sum from the current index all the way to the end, and the range sum from 0 all the way to our desired next move. Or we can just perform a range sum in this direction. But when we remove something and we want to mark this as 0 and then we still perform the range sum, now this range sum will not consider this free, so we won't overcount anything. So there is a data structure called BIT, which can exactly do what we want to do here. Basically, we want to perform the range sum while we sometimes want to multiply the value of each numbers. In this case, if we remove the current index, we want to make this value become 0. So next time we perform the range sum here, we don't consider this as a cost. So that's pretty much all of the intuition. Let's see how can we implement that in code. So first thing first, I'm just gonna write the BIT class, which we will use to calculate the range sum in order to help us to calculate the gap between our current index to our next index, as we have discussed. So I don't think we have to discuss in detail about implementation of the BIT. Even in the real interview, you just have to say to the interviewer that there is a class like BIT and assume that it exists, because I don't think the interviewer will expect you to implement it explicitly. You just need to know how to use it. I think that is already good enough. Especially in interview, there's only like 30-40 minutes. I don't think they will expect you to write the whole class and also solving a hard problem after implementing this class. So I guess it is safe to just assume it is completed in the interview. And now assume that we already completed the BIT class and we're gonna start with our algorithm. So first I'm gonna initialize a bunch of variables. To n is the length of the numbers, the position is our current position. As we mentioned, we're gonna start at position 0 and answer is the operation that we're gonna take, and we're gonna return that at the end. Now we're gonna iterate our BIT class, which will help us to calculate the range sum later on. And also we need to sort our nums because we want to know which element to visit first. So basically, which index we should visit first. That's why we have to build this helper array and then sort it, and we know the order of which index to go first. And then based on this order, notice I don't care about the first element anymore. The first element is the value of that index, but after sorting the array, we only care about the index. Now, if our next desired position is greater or equal to position, it means that we are going from left to right. So we don't have to go wrap around. That's why this is an easy case. For this easy case, and we just want to know the range sum of this current position and I. And otherwise, as we mentioned, we have to consider the range from the current position all the way to the end, and also the position from the start all the way to our next desired position. After considering all of that positions, it means that I will become the first element of the nums after performing this range sum. So we're just going to remove that and also mark this index as visited. So next time when we perform range sum, we don't want to consider I anymore, because every element start as 1, and after I perform this -1 for this index, and it will become 0. So next time I perform range sum across this I, it won't count anything. So we have to update the position to I because we move it to there. And now after doing all this, then we can just return the answer. This is a quite simple solution if we already implemented the BIT. So let's try to submit that. Okay, accepted. I think this is the best time complexity that we can come up with. So for the time, we have to do n log n, mainly coming from the sort, and also the time complexity of the BIT and doing range sum and add, etc. And the space complexity will be O(n), mainly coming from this BIT data structure and all this helper array. So that's pretty much all, and I will see you next time. Bye bye.